In this lesson, we're going to examine linear quadratic systems. That is, what happens when you combine lines with quadratics. So we're going to have two or more equations, and basically two for this point. Our objective is we want to find their point or points of intersection. And there's three ways that lines and quadratics can interact with each other, kind of like discriminant ideas. So number one, you could have 2 points of intersection. The line crosses a parabola twice. That's the maximum number of times you can cross a parabola. You could have one solution, we call this a tangent, where it just barely touches the parabola at a single point. Or you could have an inadmissible solution. There are no points of intersection. The line never crosses that parabola. Okay, so kind of like discriminant, where we had two solutions, one solution, no solutions. And we can actually use that idea to see if something's solvable before we actually try solving. We're going to approach this in two ways. Method number one is we can graph it. If we have things in mx plus b form and vertex form, graphing this solution might be pretty quick. If not, we're going to use our algebraic solutions. So we look at the first example here. The first equation is a quadratic, and it's in vertex form. The vertex is 0, -1, so we can graph that. The step pattern is a nice one. It's just the old 1, 3, 5 because there is no a value. So over 1 up 1, over 1 up 3, over 1 up 5. 1, 3, 5. And we'll get our parabola. The second equation is our line. That line has a y-intercept of 1. And it has a slope of 1 over 1. So up and to the right. So if we graph that, and graph that, we'll get our system. The solutions to the system are our points of intersection. And in this case, there's two of them. There's the one here. That's 2 and 3. And it was nice because the dots actually lined up on top of each other. And there was a second one right here at -1 and 0. As I was saying, this method is great as long as you have things in the right order. They're nice to graph, so slope-intercept in vertex form. But it causes some problems because what if it doesn't fit nicely on a graph? Or what if those points of intersections aren't actually on nice whole number coordinates? Then we're going to have ourselves a problem. So we need some algebraic methods. And to find a point of intersection algebraically, we're going to take our two functions and we're going to set them equal to each other. The idea of comparison. If they cross, they have to equal at some point. So function number one, the f function, has to equal the g function if they cross. So if we treat it as a quadratic, we know we can solve quadratics if they're equal to 0, and we put them in standard form. So I'm going to bring everything to the right-hand side, collect my like terms, and then I'm ready to solve it. We want to solve by either factoring or the formula. So x minus 1 and x minus 1, it's a simple trinomial. So my answers are either x equals 1 or x equals 1. In this case, because I have the same value, that tells me that I only have one point of intersection. Now notice I said point of intersection, right? A point is made up of a 1 and the y value. To find the y value, we can go back to our initial equations, either f or g, and figure out what's happening at 1. So either g at 1 or f at 1. I'm going to use a g at 1 because it's an easier equation to work with. And either way, I'm going to get 0. So I know my point of intersection, the single point of intersection, this is that tangent solution idea, is 1, 0. Now that one worked out nice. So if I had graphed it, it probably would have worked out nicely, but they won't always do that. That's why we want this algebraic method. Let's try the next one. Okay. Yes, it's in vertex form, and yes, it's a line, but those look like pretty big numbers for that line. So maybe the graphing method isn't the best here. Let's use our algebraic method. F at x equals g at x. Negative x plus 1 squared plus 4 has to equal at some point this equation. So I see a bracket squared. I write it out twice. I want to make it equal to 0, so I'm going to bring everything to the left-hand side. I'm going to FOIL. I can collect a few things outside the bracket already, so I'm going to do that. I'm going to distribute my negative sign into my bracket, so I'm going to multiply it in times everything, right, make sure. So I've got negative x squared, negative, I'm going to collect these two things. So negative 2x and negative 1. And one more time, collect my like terms here if I can. I'll get negative x squared minus 5x minus 10 equals 0. I'm going to try solving this. It's a quadratic. It's equal to 0. It's in standard form. I'll try factoring first. So I'm going to take out the negative 1 just to make my life a little bit easier. And then I'm going to try and man. Can I think of anything that multiplies to 10 and adds to 5? Well, no, I can't think of anything that does that. So that tells me I have to use the quadratic formula. Before I do that, however, I might want to check if this is solvable. Because if it's not solvable, there's no point actually trying to solve it. How do I check solvability? I use my discriminant. So if we try that real quick, just before we do it, I'm going to notice that I get negative 15. Well, that tells me there are no solutions. So obviously there's no POIs. Now if it turned out that I had a positive there, well, that's my number underneath the root sign. So it's a useful tool anyways, because I'm going to use it for doing my quadratic formula. But even better, it tells me I can't solve this equation. Okay, let's look at some word problems, some applications of this. Where do we come across systems of equations? So in a city park, a sprinkler waters an area with a circumference, so a circle, that can be modeled by this equation. X squared plus y squared is 20. The sprinkler is located at the origin. The path through a park can be modeled by an equation y equals 2x minus 12. A second one, a line. And I want to know, will the sprinkler spray people walking along the path? In other words, does my circle, let's pretend it's a circle, it looks more like an oval, right? My circle, does my path go through the circle so people get wet? Does it just touch the circle so they might get just a tiny bit wet? Or does it miss the circle and they don't get wet at all? Can this be solved, in other words? Are there POIs? So we're going to try this in the same way. Obviously, I'm going to use an algebraic solution this time because it's hard to draw this circle properly. And this time, I'm not going to use elimination, or sorry, comparison, where my two equations are equal to each other, because they're not set up that way. What they're really set up for is substitution. I'm going to substitute my y equation into the y value in the circle equation. So what will that look like? It'll be x squared plus, well, it says y, right? Now y is 2x minus 12. But it's got to be squared and equals 20. So now I have myself one equation with one variable. That means I can solve it. Before that, let's simplify. I see a bracket squared. Write it out twice. I want to make it equal 0, so bring the 20 over. We'll FOIL. And then we're going to collect. And then we'll have a quadratic that's ready to be solved because it'll be in standard form, 5x squared. And it's going to be equal to 0. Okay. My question wasn't, what are the solutions? My question was, are there solutions? Will the sprinkler? So do I actually care what the solutions to this are? No. I care if it can be solved. How do I check that? We use our discriminant. So b squared minus 4 times a times c. If you put that all into your calculator, I got negative 176. What does that tell me about POIs? There are no POIs. No POIs. Therefore, the sprinkler misses the path. You can walk in that path and you won't get wet. So we're using the idea of discriminant, but in a system of equations. Last one. We got Justin. He's skeet shooting. That's where you launch those clay targets and you shoot them out of the sky. Okay, so the height of the skeet, so the skeet's going to go up and then come back down. Okay, as given by this equation. The path of his bullet, he's going to try and shoot it, is given by a separate equation. Okay. We want to know how long it's going to take for the bullet to hit the skeet. So we don't know, does it hit the skeet here, the POI? Does it hit the skeet just up there? Does it hit the skeet way over here? In which case we would have two POIs. We'll have to interpret that. Okay, but we want to know how long it takes for the bullet to hit the skeet. Where are these two equations equal to each other, in other words? Where does my height of the skeet equal the height of the bullet? So we have two equations. We can set them equal to each other and solve for t. I'm going to bring everything to the right-hand side this time. So my t squared value is positive. We like positive squareds. And I want to put it in standard form, so I'm going to put the squared term first, collect my other like terms, and it's ready to be solved. Now this one I notice has decimals in it. So I could try factoring, common factoring, but I can create more decimals. So this is a situation where I might use a formula. Now I'm not checking if it has solutions because they told us in the question, where does the bullet hit the skeet? Or they're telling us that there is a solution. So we can go right to that formula. I'm solving for t, so I need the negative of b, which is right there, plus minus b squared, minus 4 times a times c, all over 2a. And we'll do the math where we can do math. So underneath the root sign, underneath the fraction, if I use my calculator for the root sign part, I got 20.25. So I can get two answers, t equals and t equals. First one I got negative 0.4, and the second one I got 0.5. Now we're talking about time, so can I have a negative time? No, that would be inadmissible. Okay, and then the second one obviously has to be our answer. So the skeet is hit after 0.5 seconds. I think there was a second part to that question too, wasn't there? How high off the ground will the skeet be when it's hit? So I want to figure out my height. Well, I have the height, h at t, or I have g at t because they're equal to at some point. Which of those two is easier to work with? I think g at t is a linear equation, right? So why wouldn't we use that one? 31.5. T. Well, we know what t is. T was g at 0.5 seconds. I believe it's plus 1 at the end, right? We plug it in there, and hopefully we get something like 16.75. Okay, there's linear and quadratic systems. We also include one with a circle on it, just to try something a little bit different. That's the last lesson in this unit. We're done quadratics. We'll work on review next, and then we'll do our test. Some questions you should probably try just to make sure you can do a little bit of solving, either by graphing or algebra, and one or two little word problems there for you.